Seniors, welcome to your last pre-calc video. Everyone else, welcome to your not last pre-calc video. So in 12.2, we're going to do these three things. We're going to divide out to find limits. We're going to rationalize to find limits. We've already kind of done the third one. And then we're going to look at one-sided limits. All right, so example 1 says find the limit of x squared minus 7x plus 12 as x over x minus 4 as x approaches 4. So first we've got to just plug it in and see what happens, see if anything crazy is going on. So if I evaluate this thing at 4, eval at 4, here's my work over here. So we got 4 squared minus 7 times 4 plus 12 over 4 minus 4. So we've got 0. I've got 16 plus 12, that's 28, minus 28, that's 0. Okay, so this guy right here is called the indeterminate form. So that means from this, just looking at it the way it is, we can't determine if there's a limit or not. So we've got to do something. And that thing that we're going to do is we're just going to factor. So if you look at the numerator, x squared minus 7x plus 12, I can factor that into x minus 4, x minus 3. You'll see the bottom is x minus 4. So if you think about this graphically, and we've talked about this before, since I have the same factor in the numerator and the denominator, that means graphically there's a hole at whatever makes that x value or whatever makes that factor equal 0. So that means there's a hole in this graph at 4. And you'll notice that that's the target that we're looking for. So even though there's a hole, we can still find the limit because we know that x minus 4 divided by x minus 4 is 1. So this, everywhere else on the graph, this simplifies to be the limit of x minus 3 as x approaches 4. So there's a hole at 4, but everywhere else, graphically, this just looks like the line x minus 3. So now I can evaluate x minus 3 if I plug in a 4. So if I plug that 4 in, 4 minus 3 gives me the limit of 1. Example 2, find the limit of x minus 7 over x cubed minus 7x squared plus 7x minus 49 as x approaches 7. Again, if we evaluate this limit at 7, or this function at 7, we end up with 0 over 0 again, the indeterminate form. So that means the way it is, we can't tell if the limit exists or what it is at 7. So we've got to do some work. So we're going to do some factoring by grouping. Some of you have heard it that way. Others of you maybe already know how to factor a cubic. We'll just do factoring by grouping here. So off to the side, we've got x minus 7 in the numerator. I look at the first two terms and pull out what they've got in common. So that's an x squared. I'm left with x minus 7. With the last two terms, see what they've got in common. Pull out a 7. I'm left with x minus 7. Okay? So, to rewrite that, I've got x minus 7 in my numerator. My denominator is x squared plus 7 times x minus 7 as x approaches 7. So again, we can see that this graph is going to have a hole at an x value of 7 because that's what makes both of these factors equal 0, and those factors are the same. So everywhere else, this graph looks like 1 over x squared plus 7. So we've got the limit as x approaches 7 of that function. So I can just evaluate it there. 1 over x squared plus 7. If I plug in a 7 for x, I've got 7 squared plus 7, so that's 56. So my limit is 1 over 56. The next method that I've got is something called rationalizing. So we've rationalized denominators before. In this example, I have to rationalize a numerator. So if we're going to find the limit of this guy, first if I plug in 0, I get 1 minus 0, which is 0. Square root of 1 is 1. 1 minus 1 is 0 over 0. So again, I've got that indeterminate form. So I've got to do something about it. So I'm going to take this function, which is 1 minus the square root of 1 minus x over x, and I'm going to multiply it by the conjugate of the numerator. The conjugate of the numerator is 1 plus 1 minus x over 1 plus 1 minus x. So now I'm just multiplying the numerator. The denominator will stay the way it is. So the denominator will be x times 1 plus the square root of 1 minus x. And then we'll figure out what we get from the numerator here. So 1 times 1 is 1. 1 times square root of 1 minus x is just square root of 1 minus x. Negative square root of 1 minus x times 1 is negative square root of 1 minus x. Negative square root of 1 minus x times positive square root of 1 minus x is negative, parentheses, 1 minus x. So these guys add to be 0. So what I've really got is 1 minus 1 plus x all over x times 1 plus 1, the square root of 1 minus x. That simplifies to be x in the numerator and x times 1 plus the square root of 1 minus x in my denominator. And that simplifies, because x divided by x is 1, that simplifies to be 1 over 1 plus the square root of 1 minus x. So that's the thing I really want to take the limit of. The limit of 1 over 1 plus the square root of 1 minus x as x approaches 0. So now if I plug in a 0, 1 minus 0 is 1, square root of 1 is 1, 1 plus 1 is 2, so my limit is just 1/2. Again, that was called rationalizing the numerator, and that allowed us to end up with a function that was equivalent, but that I could take the limit of. Next, we're going to look at limits from each side. So this example says, find the limit of f of x as x approaches 3 from the left and from the right. So we've got this function, the absolute value of x minus 3 over x minus 3. So graphically, again, we're looking at a target value of 3. So from the left side of 3, so for every value that's less than 3, if I plug in that value, I'm going to get a y value of -1. You can graph this in Desmos. You can graph it in your graphing calculator. For every x value that's greater than 3, my y value is going to be +1. And again, if I plug in 0, I get the indeterminate form again. However, now we're looking for two separate limits, one from the left and one from the right. So here's what that notation looks like. And just a side note, the limit of this function does not exist because from both sides of 3, it's approaching different y values. It's approaching -1 from the left and 1 from the right. Just gave away my answer there. So from the left, that notation looks like this. The limit of, we'll just call it f of x, as x approaches 3 from the left. Now that superscript of a minus sign means that we're approaching this target value from the left side. So a negative means from the left. So from the left side of 3, as I approach the x value of 3 from the left, I'm approaching a y value of -1. From the right, that notation looks like this. The limit of f of x as x approaches 3, so now I've got a superscript of a plus sign. That means as I approach my target value from the right. So as I approach that target from the right side, my y values are all approaching a value of 1. So I've got two different answers. From the left side, I've got a limit of -1. From the right side, I've got a limit of +1. Last example. Find the limit of f of x as x approaches -1. Here's my function. It's a piecewise function. So we've got to figure out what the graph looks like first, then we'll find the limit from both sides. So we can see graphically, and you can graph this in Desmos. For this piecewise stuff, just put the restrictions in curly brackets. Oh, those are lovely. It's been a while since I made those. Oh yeah, but you can type it in just like this. And you'll see that from the left of -1, we've got a quadratic that opens down. So it's something kind of like this. From the right of -1, we've got a line with a y-intercept at 3 and a slope of 1. So something like that. So, oh, this is just the limit of f of x, not from both, not from one side. My mistake. Okay, so we can see that from the left side, as I approach this target value of -1, our y value is approaching 2. And from the right side of -1, my graph is also approaching a y value of 2. So in this case, the limit of f of x as x approaches -1 from the left is equal to the limit of f of x as x approaches -1 from the right. And those limits, well, that's just the limit of this regular old function as x approaches -1, and that limit is 2.